are going to go a bit more advanced. Okay, we are going to look into more of quantum mechanical approach to understand the property of nuclei. But I'm not going to make it too complicated. I assume that the quantum mechanical ideas are clear to you, but still I'll just to try to keep it as simple as possible. So the last class we said that electron scattering is actually a very good tool or a very good probe to understand the property of the nuclei for the simple reason that it has got lesser mass. So the change that happens to the nuclei is going to be lesser. The nucleus does have a size. It does have an appreciable size. So it's important that the analysis procedure should be something different compared to something which is having lesser size. Okay. So what happens is there is an actual scattering of an electron. In simple words, if you have an input, and let's say that input is in the form of a wave. So we have a wave associated with the electron, and as soon as it gets scattered, that particular wave gets scattered. And if we can actually analyze and study that, that will actually give me the information on the nuclei. So actual scattering of an electron. So basically it will be a sum of the scattering from each piece of the nucleus. So what happens is, in general, when you consider a system, let's say Rutherford alpha scattering experiment, you have a gold foil. It doesn't mean that there is only one nuclei there. There are lots, millions of nuclei, right? Because the thing is, we are not considering a single nuclei. You cannot really isolate a single gold atom and then carry on the experiment. We have a gold foil. There are a number of nuclei there, and there is going to be scattering from all of them. So basically, it is a sum of scattering from each piece of the nucleus. So that is very important. And we can actually consider that that is nothing but divided into different volumes. So we can have dV1, dV2, dV3, and all of them are more or less summed up. So whenever we are considering these kind of ideas that we are doing some kind of summation, and if it is a basically a continuous summation, we come into these concepts of, let's say, integration. Okay, so summation and integration and all those things. So whenever in physics we are talking about integration and all, we are more or less shifting, so more or less the logic remains the same. So that's why electron is considered as a quantum mechanical particle. So in general, if you want to understand this, I think something which is very important is the Heisenberg's uncertainty principle, that if we have scattering within a very small region, okay, if the distance is very small, the change in momentum will be large and vice versa. So those things are important here. We're going to use that, okay. I'm just written these points, so which is important. But then we look into Mott cross section, and what is different from Rutherford's cross section is that in Rutherford's cross section we are considering only the alpha scattering. In Mott cross section, the electron scattering effect has been considered. The form more or less remains the same. Only this f theta term more or less changes, right? So the f theta term will more or less change. So this f theta term may be different, but then apart from that, charged nuclei, okay, we have z number of protons and each charge is e, so z into e will give you the entire charge of the nuclei, and this is what is Mott cross section is all about. So we did see a elaborate definition, and we did see a bigger expression for this, but in short we can say this. So this is the charge of the scattering center. So what is our scattering center? The nuclei. What is the charge of the nuclei? Z into E. I think these things are very clear to all of us. And then this is basically, which is the Mott scattering cross section, is basically a function of theta. It's quite obvious because by how much it is scattered, okay, that plays a very important role in order to understand the cross section. So that means it's a function of theta. Okay, and this entire term is called the scattering amplitude. So if we just generalize it, this scattering amplitude, this Mott scattering cross section is equal to the mod of the square of the scattering amplitude. Okay, now what is this? This has something to do with probability, because if you remember your quantum mechanics, we know that psi single-handedly doesn't have any physical significance because it does have an imaginary term and so on. But if we multiply it with psi star, we do get modulus of psi square, and that actually has got the physical significance. So what happens is this will actually give you an idea or the probability, okay, of the occurrence of a particular event. So here also we are considering this scattering amplitude. So the probability is proportional to electron wave function square. So that is very important. Okay. So in general, if we just write it down, okay, we can actually add up all the terms, okay, of all the amplitudes and just square it, okay. So this is a very general observation, but I think for your exam point of view, this equation will be important. In your exam, if I'm asking you to write down the expression for mod cross section and how it is different from Rutherford cross section, maybe you can write down that question, how it is different from Rutherford cross section. A simple answer won't be this, okay. You just simply write down this equation and explain the term. I will accept it, but if it's a 4-mark question, probably I'll give you just 1 or 2 mark or 1 mark. The important part is you write down the entire expression of mod cross section, write down the entire expression of Rutherford cross section, and show that term 1 minus sine of theta is actually the difference from the Rutherford scale. So those equations are important, okay, but this is also important to understand it in a simpler way. So then we have got a technical term which is basically called the nuclear form factor. So question is, what is nuclear form factor? Now here I would ask you to pay some attention because this is important. Nuclear form factor is something which we usually don't come across until now because this is there in the course. So nuclear form factor is not a very difficult term. What happens is if you have a nucleus and what are the change in the, let's say, the density and what are the charges present, how are the charges distributed and so on. These plays a very important role to understand the nuclear property. So this nuclear form factor which you are going to derive, okay, is going to give you an idea on this. So in general, this nucleon, since it has got a proton and a neutron, is basically having a form factor which is electromagnetic in nature because proton is charged, okay, and neutron also in to its sense is charged, okay. It has composed of quarks which are not neutral. So it describes the spatial distribution of electric charge and current inside the nucleon. So if you have the nuclear form vector, it will tell you about the spatial distribution of electric charge and current. What do you mean by spatial distribution? I've written the definition later, but still I'll explain. Spatial is something to do with space. So you have the nucleon, you have inside the proton and the neutron, so that is occupying some kind of space. In that space, how is the electric charge distributed, how is the current movement happening, and all those things will actually be nothing but determined by the nuclear form factor. And of course, this is related to the internal structure. Imagine this nuclear energy, okay, basically, or we can say that the nuclear interaction, which is known as the strongest form of interaction, acts as a very close range and they are more or less charge independent. So if two protons come very close to each other, this Coulombic repulsion is overcome by the nuclear force of attraction. So we don't have that charge experience anymore. So that means it plays a very important role, how the electric charges are distributed, how close they are and so on. Okay? So that means it will actually internal structure. Else, if Coulomb force was more than the nuclear force, this proton would have just repelled and the existence of nucleus would be there. Right? So obviously this is the additional force that we know. And then this is actually considered to be the basic observables of the nucleon. So if you're going for any kind of higher studies, let's say research work or a project, understanding the nuclear form factor, this nuclear form factor is actually one of the basic property of the nucleon. Okay, so that's very important. So anything when we talk about spatial means we are talking or occupied space, basic dictionary definition. So then I want to actually, let's say, derive the nuclear form factor. But before we can actually go for nuclear form factor, we should understand something which is called the momentum transfer. Before I proceed, I'd just like to tell you something very simple that I'll try to keep all the things from the basic. I'll try to explain the terms, okay? But sometimes if I'm giving an equation, probably derivation of that would be possible because it will take a longer time. But in this nuclear form factor, momentum transfer plays a very important role. Before I really proceed, what do you exactly mean by momentum transfer? So you have, let's say, a target, okay, and then you have a particle which is coming and hitting the target. The particle is coming with some kind of momentum, and then hitting the target. And later on, when the particle gets deflected, the momentum would be different because the chances are that the velocity would be different. So if the momentum is different, that means some momentum has been transferred to the nucleus. okay, to the target. So that is what is momentum transfer is all about. This is a very simple idea. Okay, we already know about it. Okay? But then we are just going to complicate things. Okay, we're just going to show it in a very complicated way. But I don't think it's complicated. It's simple. Okay, let's try to understand this. So if you want to study the structure of the matter, okay, if you want to actually study the structure of the matter at small distances. So it's not that you have an electron and it's hitting the nucleus and it's coming for a very far distance. Okay, relatively it's in a smaller distance. Okay, and if you consider this at smaller distance, and let's say we actually have the uncertainty principle coming into the picture. Okay, so we have got del x del p is greater than or equal to h cross by 2, which we already know from quantum mechanics. Okay? So if we actually want to prove the structure at a distance, let's say delta x, for convenience I'll just consider it to be d. Okay, d. So that is small, it still remains small. We actually need a momentum transfer. That means there is some kind of energy, momentum, which is actually getting transferred from the electron to the nucleus. Okay, it might not change the structure as such, but then there is of course some kind of effect. Okay, so then this is delta p, which is the change in momentum, is given by h cross divided by 2d. So this is the uncertainty in momentum. I think this is very simple and we know. And this is basically applicable for high momentum scattering experiment. So what do you exactly mean by high momentum scattering experiment? Okay, so if we consider scattering, I have it in my next slide, but still I'd like to explain this here. If you want to have scattering, it might be a low energy scattering or a high energy scattering. Depending on whether it's a low energy scattering or high energy scattering, your approach to solve the problem, that means to find out the unknown variable. For example, if you consider a Schrodinger equation and then you have got, let's say, the normalization constant A. So that is an unknown variable to you. You do some probabilistic maths, okay, you do some integration and you find out what is the value of A. That is the approach that we already know, okay, use the normalization condition and so on. So this is the approach that we use. Similarly, if you consider a scattering experiment, it might be a high momentum scattering experiment or a low momentum scattering experiment. Depending on what kind of scattering experiment you are considering, your approach would be different. That is what quantum mechanics teaches. Okay, so you already know about Born approximation, and then there is also something which is called partial wave analysis. Okay, so this is something which you are going to see. So high momentum scattering experiment is going to happen, which is important. But before that, let's just look into this very simple diagram. I think this is clear to you. We have an electron and it has got a momentum of pi, which is the initial momentum, and it is basically coming from a short distance, not from a very large distance, and hitting the target. What's our target in this case? The target in this case is basically nothing but the nucleus. And then after it hits the target, it gets deflected. Let's say theta, if we just consider this to be the original axis of motion. So it gets reflected by an angle theta, and the final momentum is Pm. Now, since momentum is mass into velocity, it's a vector quantity. So we already know about vectors. If this is the vector direction and this is also the vector direction, without changing the direction, I can take this at this particular point. So I can consider this Pi here, and then this Pf is here. Okay, so this will be my theta. So once we have these equations, we can actually find out we by using the vector calculus, right? So it is very simple. So this is your theta, and so once we have this, what we have is this, and then we can actually know what is the change. So if you join these two vectors, or the difference between these two vectors is going to give you the change. Of course, we assume or we understand that the momentum is transferred to the target. So initial momentum would be more, and the final momentum would be less. So that means the momentum that we have is nothing but Pi minus P. So this is the momentum transfer expression. Now, when we actually do some numericals or you come across different books, there are different ways of writing this momentum. Okay? So we are just going to look into two forms of writing the momentum. Okay? So this is important, okay, even for your exam also, this might be an objective question. So I'll just give you a representative forms of the momentum transfer. There are two ways of writing this out. First thing we already know, Q is equal to Pi minus Pf, very simple. The first form, okay, that I'm going to say is the previous one is a simpler one, but here the first form that I'm going to talk about is this. This q bar. Please remember, q bar is not charge. Okay, this is just a change in momentum. This is just a notation that is used. Okay, so don't get confused here. So q bar, okay, this is a vector, can also be written as k bar minus k bar dash, which is equal to 1 divided by h cross into p bar minus p bar dash. H cross is just, we can, in general we say that H cross, we know that 6.64 10 to the power minus 34 joule second. So sometimes what happens is when we are considering something in quantum mechanical regime, we consider H cross more and more, okay? And when we have H cross, we are talking about in terms of quantum mechanics, first point. Second thing, sometimes the unit is also measured in terms of H cross. The other class I also told you HC, okay? So these are all possibilities that is there. So quantum mechanics and relativity you mix, okay? And then you can basically get relativistic quantum mechanics. So whenever you talk about relativistic quantum mechanics, you cannot ignore H, you cannot ignore C, okay? Very important. Here, this is the form that we have. We get this form. I think this is very simple. I'll just written it in one para. So you know that K is basically nothing but the wave number. We have an electron coming and hitting the nuclei and getting deflected. We are talking about the uncertainty principle. We are talking about the de Broglie wavelength associated with it. So definitely K will actually represent the wavelength or wave number. Okay, and then if we represent something in terms of lambda, we are representing the wave of that electron. Very simple. So we have got K is equal to 2 pi divided by lambda. So we can simply write it down. Q is equal to, we can use this expression. Okay, we'll arrive at this expression. So you see, if you use this expression, what we can do is we can write down 2 pi into 1 by lambda minus 1 by lambda dash. You can do the maths. I think this is very simple. From de Broglie's wavelength, we already know lambda is equal to h divided by p. Okay, or we can write down. Okay, so there should be an implies there. Sorry. So this is there, and then this implies that 1 divided by lambda is equal to p divided by h. So this is 1 divided by lambda. We can just replace it p by h minus p dash by h. Let's not get confused here. P is nothing but the momentum, initial momentum, and p dash I'm representing as the final momentum. You can write down pi and pf, doesn't matter. It's all the same. So then what we can do is 2 pi divided by h, I can take it out, and then this will be nothing but p bar minus p bar dash. So 2 pi I can just bring it here. Okay, so if you just bring this 2 pi here at the bottom, just divide it by 2 pi. So this will nothing but become here h cross. So it will be simply 1 by h cross into p bar minus p dash, which essentially represents the same thing, but it's in terms of h cross. That's all. Okay. So this is there. There is one more form which is used, okay, but this is also not very complicated. The second form is this, okay. The second form is this. This is the form that we are going to derive now. This is also very simple. This q, okay, the modulus of q, the modulus of momentum transfer magnitude is this. Here we assume something. We assume that electron is actually a very light particle. The mass is 10 to the power minus 31, so very light. So we can consider that the initial momentum and the final momentum are almost equal. Not equal, you know that we do a lot of assumption in physics, and sometimes we see that if we do that assumption, the equation becomes simpler, okay? So we'll assume that Pi and Pf are almost equal. So the question is, if it is almost equal, we will say that this particular equation should become zero. This particular equation should become zero. The question is, this and this approaches towards each other. It's not that they are equal, okay? So that's why we're going to take a different approach to solve this mathematically. So what we do is, we consider Pi is almost equal to Pf. So we just take the dot product of Pi dot Pf. We can just Pi Pf cos theta. Since Pi and Pf are almost equal, we can just assume it to be modulus of P square into cos of theta. Now we will square it, okay? Our aim is to find out what is Pi minus Pf. So in general, if I consider them to be equal, this becomes zero, which is not the case, okay? There is some kind of transfer, but the transfer is very less, okay? We are going to see this. So if you consider Pi minus Pf whole square, just x, then this will be a dot product. So it will be Pi square plus Pf square minus 2 Pi Pf cos theta. So you can just consider this and this to be equal to P. So 2p square minus 2p square cos theta, we are considering Pi is equal to Pf, and then 2p square and minus 2p square, and this cos theta we know can be written in terms of half angle, okay. So I think we already know this, cos of 2 theta is equal to 1 minus 2 sin square theta. So this is 1 minus 2 sine square theta, and then we can write down cos theta is equal to 1 minus 2 sine square theta divided by 2. Okay, so this I think is simple. I can divide throughout by 2 here and here also. So half angle should not be very confusing for you, basic trigonometry. Just replacing it here, and then I can take 2p square common, so 1 remains from here, and then this is minus 1, okay, and then plus 2p sine square theta. So you can do the maths. I think it's better you practice on your own and find out the final result. Don't just compare step by step to whatever I have done. Okay, you might maybe a different way. You can do it faster also. So the final result is 4p square sine square theta. So if you just take the mod of this, okay, you can take the square root on this side, you can take the square root on this side, simply have 2p sine of theta divided by 2. Now imagine this, this is one more form of momentum transfer. So if you basically consider theta to be 0, okay, if theta is 0 and then sine is nothing but 0, right? And then if theta is 90, basically sine is 1. So what happens is, if this theta increases, okay, if this theta increases, P minus Pf, that means Q will also increase. Analyze this result, okay. This Q will also increase. What does it say? That if theta increases, there is going to be more deflection, and if there is more deflection, there is going to be more and more momentum transfer possible. Okay. So this is the logic that we stand at finally, assuming Pi and Pf are very close to each other. Very important. Okay, so these are the two forms of momentum transfer, and then we will get back to nuclear form factor. But before that, let's try to understand that for finding out nuclear form factor, we have to use Born approximation. The question is, why Born approximation? Assuming that you and me don't remember everything very clearly about Born approximation, I have just made this one slide with a lot of information. Okay, in exam, please don't write down in this tabulated form. If I'm asking you a question, why we use Born approximation in case of electron scattering, please try to frame some sentences. Okay, try to make it logical. That's more important. Forget about the grammar. वो थोड़ा गड़बड़ हुआ, I consider no problem. Okay, but try to understand what I'm trying to explain here. Okay, it took me some time to prepare this slide because I was thinking how to make it simple. So if you consider scattering, after scattering happens, you can actually have plane wave or you can have a spherical scattered wave. It depends on what is the velocity of the incoming particle. So let's say the electron is coming and hitting the target. After it gets deflected or basically gets scattered, you will be actually having a plane wave and the spherical scattered wave. So try to understand this. When we basically consider a plane wave, I think all of you know about wavefront. Okay, so what happens in wavefront is this: you have a wave, and then if it is coming from a very infinite distance, you know that there are waves which are coming, and then if there are a number of waves which are coming, they are more or less plane waves. Okay, so the plane, it's basically called a plane wavefront. What happens is you can actually join these peaks, okay, and then you can see that this will actually form a plane wavefront. So this is a plane wavefront. On the other hand, if you consider a spherical wavefront, in general you can consider a point source, and you will be having a wave coming in all directions, okay, and then this will be there, this will be there, and then this will be there, and then we have got this equal to there. And then what happens is, if you consider a 3D image and join the points of maxima, you're going to get a sphere. So that is a spherically scattered wave. Okay. So what happens with plane wave, what happens with scattered spherical scattered wave is something which is more preliminary. So when there is scattering, outgoing waves will both have a plane wave form and a spherical wave form. But then I want to have only a plane waveform. Okay, what will be the condition? The condition would be that the incoming wave, or that means the incoming electron in our case, will move very fast. So if it moves very fast, it gets scattered and the output result would be a plane wave. Okay. So if you consider in general a scattering experiment, it can have two parts. Okay. This is the probability that there will be two parts. One will be basically a plane wave and the second one will be a spherically scattered wave. So then since we are not doing basic physics, we are into advanced physics, it's important to write them in the form of an equation. So plane wave can be written in this form: a to the power I k dot r. I think this is very much quantum mechanics. Okay, I think you have already studied this. Okay, so this is there. And if you write on a spherical wave, you actually have a term f theta phi. You know that r theta phi will actually define a spherical coordinate system. So if you basically have a spherical coordinate system, you need r, you need theta, you need phi, all three. So basically, a spherical scattered wave should have this form. This is very much logical. Okay, if you have understood our lower class geometry, this should not be very difficult to understand. But if you consider a plane wave, the variation will be only in terms of r. That's important. So this is the outgoing wave that we have in a scattering experiment. We are studying scattering, so these things are important. So there are two ways of analysis. Okay, one is basically called the partial wave method, and one is called the Born approximation method. Okay, so if you consider the partial wave method, there are certain conditions under which this particular approach is used to study the outgoing wave. First thing, it's a central potential. VR potential is of R is from the potential now. See, basically what happens is nuclei has a charge. So if you are having an electron and you want to bring that electron from that point to near the nuclei, you have to do some kind of work. Okay, and that means there is some kind of potential which is involved here. Okay, so that is the reason we are talking about potential. So if it is not charged, the potential factor will more or less be avoided. Okay, we actually don't need it because it won't hold any potential. So charge is there, so potential is a very important term that actually defines the entire process. It's a short range potential. Okay? So it's not that it will act for a very large distance. Okay, so if you consider this partial wave method, it's basically a short range potential. And then this actually results in low energy scattering. Low energy scattering. So in case of electron, when it is coming and hitting the nuclei, we are not talking about low energy scattering, we are talking about a high energy scattering. So that means this particular approach will not work for this particular analysis, and hence we are going to use Born approximation. What does Born approximation say? The first point is used when incident wave is not distorted too much. You have a wave coming, hitting the target, getting deflected at a high energy. So if it is coming slow, the distortion will be more. If there is distortion, there will be more and more spherical scattered waves. Okay, so that means in Born approximation, we are considering the plane wave more or less. Okay, VR, which is the central potential, is weak. But then VR might not be central, okay, because it might depend on the distance. It will other factors. So this is what. So if we have a function, okay, and then f theta phi, okay, can be approximated using the Born approximation. Okay, so we'll just take fb1, okay, and then what happens is we are considering Born approximation and it's a plane wave, so more or less the function will be r dependent and not mostly theta phi. Okay, that's the representation of this. So we can actually take the value here. Okay, we can use the bracket function. We already know about these things from quantum mechanics. So we can actually find out the probability. So what happens is I will basically integrate it. I will take the final wave function, and this is your initial wave function, and we are going to find out the potential. But I don't know what is the potential till now, so I'm just going to consider a form. Okay, I'm going to assume a form. Okay, and then of course we are considering it in a three-dimensional space, so D3R. So this is something which should be from quantum mechanics, which is from quantum mechanics, very important. So if we use the first approximation, we have got the initial incoming wave and the outgoing wave, and both are assumed to be plane waves. So if it is a plane wave, we know the form e to the power I ki dot r and e to the power I kf dot r. Okay, this is why I've given you that scattering slide to understand the difference between a plane wave and a spherical wave, and why we are considering a plane wave. We are considering a plane wave because we are considering approximation. Okay, so then we can actually know that there is some kind of momentum transfer. Okay, because this is the incoming wave and this is the outgoing wave. There is a momentum transfer and this is the momentum transfer relation. So we already know about this. Since we are writing down in terms of Ki and Kf, I have derived that relation in terms of Ki and Kf, momentum transfer, so that you are not confused. Okay, so whether you write it down as Ki minus Kf or you write it down as Pi minus Pf, more or less both of them sets in the same meaning, the same physical meaning. Only the difference is there will be an H cross del in place of K. So in terms of H cross difference. So if we just replace this, okay, it's becoming simpler now. E to the power minus Kf dot r minus, okay, and then this is nothing but e to the power I k I f d theta dr. So we have this. You can just bases are same, powers can be added. So you can just take ki minus kf dr d3r. So we have simplified the relation in this way. We already know that ki minus kf is nothing but q. So we have simplified this. Okay, we have simplified this. Should not be very complicated for you to understand. And then what we do is we want to know what is the form of this potential. We don't know how does the potential look. Okay, so we want to find out what is the form of the potential. The potential is obviously dependent on the charge. Okay, because these are charged centers. So the potential might be weak or might be strong, but still there is potential. Okay, so that means we have to consider this. So we basically consider the basic chapter on electrostatic potential of plus 12 or maybe plus 11 you studied. You basically have potential as 1 by 4 by epsilon naught into, which is k of course, and then this is nothing but charge 1 charge 2 divided by r. Okay, so what was my charge 1? Charge of the electron, so that's E. What is the charge of the nucleus? Z into E. So it takes Z E into E, so it will be Z E square divided by R. So we have got Z E square divided by R divided by 4 pi epsilon naught. But then that was the idea we had it at that time. Okay, and that time we are just considering assuming two charges and they are moving and they are having some kind of interaction. But the real world is not that simple. There are more complexities. Okay, so we have the charge density and all those stuffs. Okay, how are the charge distributed and so on. So this particular expression will give you the information about the charge distribution. This r minus r dash is the same. Okay, this is this r only, because we are differentiating with respect to r dash, so we are just taking it inside the integration sign. These terms are constant. So these terms are constant. So we have basically got a charge distribution term and then divided by r minus r dash, and then we can actually integrate it to look into the real world picture. So this is actually nothing but welcome to the real world. Okay, it's nothing but more practical in nature, because this is what is the research work. Okay, start from basic and then you shift there. So what we can do is we can substitute 2 in 1. What was our one? Our one was this, which did not have any kind of potential involved. So we replace this equation 2 in equation 1. So we're just going to replace it. This will remain there. This is already there, okay, and then there is a D3R term. Where does this term come from? This one, this term is there, and then we can just sorry, yeah. So we have this, and e to the power I q bar dot r is also there. Okay, so both these terms are there. Okay, and then from here we can actually get the form factor. So we can actually do some substitution. Even if we don't do the substitution, still we can actually get the form factor. Okay, if you do the substitution is like r bar minus r bar dash. So basically it is nothing but the in the initial frame, and this is in the final frame. So that means this is after the scattering happens. This is before the scattering happens. So obviously if I take r minus r dash, just like we took p minus p dash is equal to q, r minus r dash can be considered as capital R. Okay, just a representative form, or small r can be written as capital R plus r dash. Okay, so that is nothing but, let's say, the part difference kind of factor. So we can just simply write it down e to the power I q dot r, which is equal to e to the power I q bar dot small r can be written as capital R plus r dash, and then I can separate it out. Very simple. We'll just try to improvise here. Okay, we'll try to improvise here. There is a term d3r here. Sorry. There is a term d3r. Missed it out. Okay, so term d3r is there, and then we have got the remaining factor. If you look into the previous problem, previous slide, we have actually not changed much. We have just taken this d3r here, okay, and then we have replaced this r bar minus r dash. Okay, if we replace this, do the sum here. Okay, we can actually do that, and then we can simply represent this r as r bar plus r bar dash. So if you can look here, this is your r, and you replace it with r bar plus r bar dash, so you get two different terms. This is one term, sorry, this is one term, and this is one term. So I think this is simple maths. It's not take too much time here. This particular term is called the form factor. What information does it have? Look here. This is r dash. That means what is happening to the wave after it suffers scattering. That is why there is an r dash. So we are studying the effect after scattering. This is the charge density. Okay, and that is also dependent on r dash, and then of course in terms of r dash coordinates. So this particular term is called the form factor.